Hello. Welcome back. Last time we talked about waves. We talked about the different parts of a wave that you might need to know. Here's our little wave diagram up here. We talked about these terms: amplitude, frequency, and wavelength, and how they can be attributed to different kinds of waves. Remember, those things aren't exclusive to light waves. They can be attributed to any kind of wave, a wave in water, earthquake, seismic waves, sound waves. But in this class, we're going to be focusing a lot more on the light waves because that's what we use in astronomy. We also talked about the speed of light. We've got a couple of numbers down here that have to do with the speed of light. Remember, light travels at 300 million meters per second or 186,000 miles per hour. Very, very fast. Which is good for us because space is very, very big. So we use the speed of light to measure how far away things are. Remember, we use light speed. So if light travels 300 million meters per second, however far it can travel in a year is one light year. We use that to measure distances out in outer space. Today we're going to be talking about the electromagnetic spectrum, and you may have seen this image or an image like it in the past. It shows you different. Where should I be? Up here? Sure. It shows you different types of electromagnetic waves. Now, we as human beings are only able to see certain types of light. The different colors of light that you might see when light reflects off of different objects out in the universe, they give off different styles of different wavelengths of light. And so some wavelengths we're able to see, and then some stuff is outside of our eyes' range of vision. The wavelengths that you can see here, they start out relatively long and then they get shorter and shorter and shorter. So it's a scale going from low energy waves and then getting more and more energy as I'm backwards here. Low energy waves and then it gets more and more high energy as the scale goes on. So we'll talk about the low energy stuff first. No, sorry, my camera is backwards. We'll talk about the low energy stuff first, and then we'll go up the scale here and end up with the high energy stuff over here. In outer space, this is the stuff that can be nasty and dangerous. So that's the more fun stuff. All right, let's start with like that there. Let's start with that stuff. On the weaker end of things, this is not something that we can see, but it's stuff that's around you all the time. They're radio waves. And yes, just like the waves that get beamed from the radio station to your car, these are long wavelengths and not very high frequency, meaning there's not a lot of the waves. So they're low energy. It's exactly what you know and love. Then, as we go up the line, we get to microwaves, also not visible, but a little bit more power. Shorter wavelength, ever so slightly, higher frequency, there's more waves, a little bit stronger power. Infrared waves, which we have right here, this is what heat gives off infrared waves. Also, not something that you can see, but it is a type of light that some organisms are able to see. And we do have like heat sensing cameras, infrared cameras that are able to take pictures of objects using their heat, taking in infrared waves. Let me just see if I can pull up an image. No doubt you've seen one of these before. An infrared image. Boop, boop, boop. Here's a guy. Obviously, you don't see real life like this, but this is a camera that is taking an image with looking at infrared radiation. It's looking at an infrared wavelength instead of looking at just the visual light. If this were visual light, we'd just see the guy's regular skin and his regular eye colors and his mustache. But this is a camera specifically looking at the infrared radiation that's coming off of this guy. This is his heat. All right. Now, that's just barely too long of a wavelength for our eyes to see. After the infrared radiation, we have a very specific band of light very specific wavelengths that our eyes are able to see. And this also has a spectrum, that the long wavelength stuff is red colored. And then when we get to the end of the visible light spectrum, uh, those blue colors, those bluish purples, have a shorter wavelength. So whenever you look at the colors of anything, depending on the wavelength of the light that's bouncing off of it, that's what causes your eyes to register it as red or as blue or as green or as yellow, right? So, let's see if I can find some stuff. I have my cup or my shirt. My cup is bouncing off relatively low wavelength stuff. Sorry, relatively long wavelength light, because it's red and that's bouncing off and coming into your eyes, right? Something blue, something blue. I don't want to show you my car. Ah, here's an IKEA bag. It's blue. The light that's bouncing off of it is short wavelength and it has a little bit more energy. Obviously, it's not a dangerous amount of energy, because if that were the case, we would be getting cancer from stuff that's blue. But you know that that's not the case. That said, blue wavelengths of light are shorter than red, and they have a little bit more energy. Not enough to make it so that it's dangerous, but it is a little bit more. As the wavelengths are getting shorter and shorter and shorter, eventually we're going to reach a point where the wavelength is just too short for our eyes to see anymore. It gets out of the visible light spectrum and goes further this way along our spectrum here, outside of the visible light and into the ultraviolet. You maybe have heard this term before. This is the nasty stuff that comes from the sun, right? It's the reason why you wear sunscreen when you go to the beach, to protect your skin, protect your body from the ultraviolet radiation. That's exactly what this is. This is radiation. All of these are radiation. It's just now we're getting into the dangerous radiation. Ultraviolet light waves are short wavelength, and it's getting more and more energy. It's getting to the point where now it's starting to get into the dangerous stuff, especially if you have a lot of it. So that's UV radiation. Moving further along, we get to X-ray radiation, which you may have experienced if you go to the dentist, or if you have broken your leg or something. You may have had to go and get an X-ray. It's along the electromagnetic light spectrum, more and more dangerous. That's why they put the plating in front of your face, or in between you and the X-ray machine, and it's why the doctor runs out of the room when they go to hit the button, because they don't want to get beamed by it. Dangerous stuff, but useful in the medical field. Then we get even further along. We get into very short wavelength, extremely high energy stuff, gamma radiation. Extremely dangerous, extremely lethal. Lots of energy here. The particles are moving very, very quickly. Short wavelength, high frequency, nasty, nasty stuff. All of this from radio, I keep going backwards, from radio waves to gamma waves are radiation. It's all light. It's just there's a very small little part of this spectrum from one end to the next that we're able to actually see, that visible light spectrum. If the wavelength is too long, it's outside of our vision. If it's too short, it's outside of our vision. It's just the short wavelengths are dangerous for us. The long wavelengths, not so much. That's the electromagnetic spectrum. Our next video, our last one on waves, we'll talk about the Doppler effect, which is something you may be familiar with. If not, we're going to talk about it then. Of course, if you have questions, please feel free to ask. Happy to help. I'll see you then. Adios.